This is an exothermic reactor system that's unstable. We have reactor feed stream with product stream, and we have our cooling flow and our cooling water exit. Right here we have an inlet temperature of that cooling water, and then it's going to come in, fill up this, go mix in here with the jacket, and then come out, and that's going to cool the reactor. And we have a transfer function that relates the temperature of the reactor to the cooling flow rate. Now you'll notice here we have a root that says it's 1/2. That means it's going to be unstable if we have a positive real root. We have another one that's s equals -1, but that we only need one that's positive real to make it unstable. So we have a control system where we have a temperature transmitter, and then we have our temperature controller. That's just going to be a proportional only controller. And then we also have something that converts a milliamp signal into a PSIG signal that's going to operate the valve. Now this is going to be a fail open valve right here. So in case of loss of pressure, that valve is going to open and provide cooling flow to the reactor. So let's go ahead and just develop this as a block diagram and then fill in the different pieces that are needed for our system. So I have my temperature set point. That's going to be coming into this controller right here. And then I'm going to need to convert that with a gain into a milliamp signal. And you'll see why I do that. I'll put that as a tilde. Okay, this is going to be a degrees Fahrenheit, and then I'll compare that. Let me put a comparator here. I'm going to put an add and subtract there, and this is going to be my error. And that's going to be my error between my measured value, and that's going to be my temperature. I'll put that as a temperature tilde. And we get that measurement by having a transfer function between the measured value of temperature and converting that into a milliamp signal. So here's degrees Fahrenheit for my temperature, and I convert that into a signal, in this case a 4 to 20 milliamp signal. And then that gets compared, and then I have an error. That error is going to be multiplied by a gain, Kc, and that's going to be in milliamps as well. Now I need to send that to a valve. Okay, this is going to be my valve, and then here is my process. Okay, and in order to get it to the valve that needs a PSIG signal, a pressure signal to move that valve, I need to have a KIP. So that converts my current into a pressure, and then I'll have a valve transfer function and then my process transfer function. So I need all of these individual pieces in order to be able to do the stability analysis. Let's see if we can get these individual pieces from the problem statement. So the valve on the cooling water inlet fails in the open position, air to close, and passes 360 gallons per minute of water when completely open. Okay, so we have a 3 to 15 PSIG signal that's going to be used as typical for operating valves. And when it is equal to, let's go ahead and just get this, the flow rate is going to be equal to 360 gallons per minute when it is fully, this is going to be equal to 3 PSIG. So when the pressure is off of the valve, it's going to be open. And when it is fully closed, then it's going to be 0 gallons per minute, and that's going to be equal to 15 PSIG. Okay, so when we apply pressure to it, it closes the valve, and that gives us something that looks like 360 gallons per minute divided by -12 PSIG. Okay, so if we just do the math on that, that equals negative 30. That's going to be negative 30, and that's gallons per minute per PSIG. Okay, that's our block here. It's going to go right up in here in our, that's going to be our valve. Okay, negative 30. Okay, and then we also had our process transfer function. There's GP right here. That's going to go right up here into the GP location. Let's go ahead and go through our problem a little bit more and see what else we can find. You may assume that the pressure drop across the valve is constant, that valve dynamics are negligible, and that the valve is linear. So that's why we can use a kV value, just a simple gain for our valve. The temperature transmitter has a range of 200 to 400 degrees Fahrenheit and requires about 0.5 minutes for a reading to reach its final value. So, for example, let's say we had our temperature in our reactor instantaneously change. Then we would have our measurement, our measurement device would also need to heat up as well. And it would get, in one time constant, that would be 1 times tau, we'd get 63% of the way there. 2 time constants, about 83. 95 after 3 time constants, and then you'll be 99.5 after 5 time constants. Okay, so we just say it takes about, that's about 0.5 minutes. Okay, I'm going to use the 5 tau there to get my, that's going to be my tau of my measurement is going to be equal to 5 tau of my measurement is going to be 0.5 minutes. So tau of measurement equals about 0.1 minute. You could also use the 3 tau there if you wanted to. Okay, so there's my time constant for my measurement device. Let's see if we can get the gain from it as well. We had the 200 to 400 degrees Fahrenheit. And we can assume a 4 to 20 milliamp signal for the 200 to 400. So let's go and get our measurement gain. And so if we have something that we need to convert into milliamp, at 20 milliamps, we're going to be seeing a 400 degree Fahrenheit temperature. And at 4 milliamps, we'll see 200. It'll be 200 degrees Fahrenheit. Milliamp. Okay, so we have our 16 divided by 200, and that's going to be milliamp per degree Fahrenheit, and that is going to be equal to 0.08. Okay, milliamp per degree Fahrenheit. Okay, so this is just a first order approximation with measurement dynamics. Okay, so Gm is going to be equal to Km divided by tau m s plus 1, and that's 0.08 divided by 0.1 s plus 1. So that's that block right there. Now, one of the things that we need to do is so we can compare, milliamps here to milliamps there for our air, is we need to convert the temperature set point right here into a milliamp. And the way we do that is we just take the measurement gain. Okay, to convert that into a milliamp, so we'll put that, the same Km that was used down here, we'll also insert that right up there. Okay, so let's continue on now. We've got our measurement transfer function, we have our valve transfer function, and we need our KIP as well. We need to convert, let's see if we, okay, so we need this one that converts the milliamp into a pressure signal. And so we're just going to use the standard industrial process control values. So in order to get a pressure at 15 psig, we're going to have 20 milliamps. and at 3 psig we'll have 4 milliamp. Okay, so the upper and lower typical limits. And so that's going to give us 12 divided by 16. That's going to be psig divided by milliamp. Okay, and that's going to give us 0.75 psig divided by milliamp. Okay, so we have all of the individual pieces now. Now we just need to get a closed loop transfer function. So here are all the individual pieces. So closed loop transfer function is going to be equal to, one of the ways I like to do this is do direct divided by 1 plus the loop. That's kind of a shortcut way. You could also do block diagram algebra, but basically I want to get a transfer function between temperature set point to temperature. Okay, so that's going to be temperature set point, the relationship between temperature and temperature set point. And to do that, I'll just multiply all of the things that are in the direct line between those, and then 1 plus whatever is in the loop. So direct is going to be Km, Kc, Kip, Kv, and Gp. And divided by 1 plus the loop, 1 plus, and then everything else is going to be the same except you have a Gm there. A Kc, Kip, Kv, and Gp. Okay, so here are all of our pieces. Let's see if we can write all those out. We have 0.08. Okay, Kc, we're just going to leave that as a variable. And then 0.75. Okay, and then Kv, let's see if I can get this, was going to be equal to -30. And then Gp is just going to be the transfer function that was given to us. And that's -0.7 divided by s plus 1 times 2s minus 1. Okay, and then that's going to be Gp. Okay, and then I'll just same thing on the bottom, except that we're going to have some measurement dynamics in addition to the 0.08, 0.1 s plus 1. Okay, and the rest of it is going to be the same. Okay, let's go ahead and just multiply through our polynomials. So I'll go ahead and multiply the numerator and the denominator by s plus 1 times 2s minus 1, and also throw in there the 0.1 s plus 1. So just multiplying the numerator and denominator by the same things. These are going to cancel out. Right here, right there, and then they'll also cancel these terms, but I'll have to multiply this over by that 1. Okay, so I'll have 0.08 times Kc times 0.75 times -30, okay, times 0, I guess I'll have another negative there, that'll cancel this one, 0.7, and then times 0.1 s plus 1. Okay, that's going to be the numerator, and then our denominator, okay, and then the remaining terms there. And okay, so here's our closed loop transfer function. We need to really just look at the denominator for stability. So let's go ahead and just write this out. If we multiply this out right here, we're going to have 2s squared plus s minus 1, and then I'll multiply that by 0.1 s plus 1. Okay, and that'll give me 0.2 s cubed plus 2s squared plus 0.1 s squared plus s plus, I'll put a minus there, minus 0.1 s minus 1. If I add up all of those, I'll have 0.2 s cubed plus 2.1 s squared plus 0.9 s minus 1. Okay, and then if I take all of these and multiply them together, then that's going to give me plus 1.26 kc. So here's my polynomial in just from the denominator, and I'll set that equal to 0 and find the roots of that. And when any of the real parts are positive, then I'll know it's unstable. So let's use the Routh array method to be able to calculate the stability. I'm going to make this just a little bit bigger. Here's the homework problem right here. But if you come up to the link at the top, the background information on stability analysis, you'll see the Routh array method. Okay, so we're going to create this matrix and then look for where the leading left edge is going to be positive. So I'll do 0.2, 2.1, 0.9, and then -1 plus 1.26 kc. Okay, let me calculate B1, and then I'll also calculate C1 as well. The others here are going to be 0. Okay, if they're not there, just going to assume 0 here in the upper part, and those will make zeros down below as well. So to do this, I'm going to multiply this by that, and that minus that times that, divided by the 2.1, and so B1 is going to be equal to 2.1 times 0.9 minus 0.2 times -1 plus 1.26 kc divided by 2.1. And then C1 is going to be equal to, okay, B1 times -1 plus 1.26 kc, and then I have minus 2.1 times 0 divided by B1. So C1 is just going to be equal to -1 plus 1.26 kc. Okay, and the other ones are going to be 0, as I mentioned. So we want to look at the leading left edge, and if it changes signs, then it means it's going to be unstable. So this one is positive, that's positive, so B1 needs to be positive and C1 needs to be positive as well for this to be stable. So I'll say that's greater than 0, and this one has got to be greater than 0 as well. Hopefully that'll give us the upper and lower limits of our stability. So if I just multiply this out, I get 1.89 plus 0.2 minus 0.252 times kc, and I'll divide that by 2.1, and that has to be greater than 0. And if I then just do the math on this, don't forget if you divide by a negative value, that's going to switch directions on the inequality. So kc has got to be less than 8.29. That's an upper limit on our controller game. And then if I do the same here, I'll get a KC has got to be greater than 0.79. Okay, there's a lower limit. So we've calculated the upper and lower limits. It's got to be less than 8.29 and has got to be greater than 0.79. Okay, let's just test this out though. We want to see how this is going to respond, and so let's just you'll use the signal package within, we'll use the signal package within Python just to be able to simulate this. And so I'll import NumPy. Okay, I'm just going to use NumPy and then the signal package from SciPy. Those are the two that I'll use. I'll also bring up a root locus plot that we can look at as NP, and then I'll do let's see, I'll do import or from SciPy import signal, and then import matplotlib pyplot as PLT. Okay, and let's just save this as a I'll call this stability.py. Okay, so the very first thing I'll need to do is just say, what is my numerator? And let's go back to my numerator. Okay, it was up there at the top. So numerator is going to be 0.08 times 0.75 times 30 times 0.7 times 0.1. Okay, that's going to be the S term. And then I'll also have that same thing except no 0.1 there for my second term of my polynomial. Okay, I guess I could have computed this earlier. A and A. Okay, there I go. I have, and then my denominator. Okay, that's going to be I have to have my KC here now, just to be able to say what that is going to be. Let's go ahead and select something that's kind of in between there, and then we'll change KC and analyze the stability. So we have our denominator term now, and I'm just going to use the one that I have circled there with my polynomial values 0.2, 2.1, 0.9, and then minus 1 plus 1.26 times KC. Okay, so there's my denominator, and then I'll use my signal package with my I guess I gotta do dot transfer function with my numerator and denominator terms, and then I'll get my response by using signal dot step, and I'll step this system that I have, and then I'll plot it. Okay, and I can plot t comma y. Okay, so let's just do our this is our step response with our controller of KC equals 1. And let's go ahead and just open this up with IDLE, or you could use Spider or Jupyter Notebook as well. And I'm going to go ahead and run this, and I think I forgot to do the show at the end. Okay, so let me do that. plt.show. Okay, so let's see if this is stable. Should be a stable response here. Okay, a little bit of overshoot, and let's go ahead and change our controller again. We're going to go to it was 0.79. Let's get the stability limits here and just test those. Okay, so we're at 0.79, and I'll run that, and this should be right on the stability limit. Okay, and if I just do it a little bit higher, like 0.8, then it should be stable. Okay, so it is stable. And then, but that's a bad control. You can see it, the reactor went to a very high value. I had a step of 1 in my temperature set point, so I might need to have a higher controller gain. So let's put this up near 6 and just see what that goes to. Okay, so it's going to be stable, but again you can see the oscillations. And if I go to 8.3, it should be unstable. It should oscillate out of control. Okay, so there you can see it's diverging. So we had approximately, good limits here. We just tested them with simulation. We might want to have something like a controller with KC2, for example. Okay, so there's our controller, fairly aggressive, KC2. If I had something like 1 point, let's just do 1 and see if that gives us a better response. Okay, so there's still a lot of offset there, but let's go in and just do a root locus plot as well. You could do this with you could do this with Python. I really like MATLAB for this one, for the root locus plot. So I'll just show it to you briefly in MATLAB, but you can do the same analysis in Python. It's just the plot isn't quite as interactive as it is in MATLAB. So let's just try this. I'll just open up MATLAB. I'll create this transfer function, and then we'll just do the in MATLAB, what you have to do for the root locus, you have to just input the open loop transfer function. So I'll just put in the open loop, and that's going to be right here at the very top. Okay, our open loop would just be the the numerator, or I guess the loop part of it. Okay, and so let's go ahead and just okay, and here we go. I'll just clear the screen and make a new transfer function variable s, and I'll have my open loop transfer function, and I'll just multiply these out. 0.1 times s plus 1 times, I'll just leave off the kc there. Okay, and then have negative 0.7 divided by s plus 1 times s, 2 times s minus 1. Okay, so there's my open loop transfer function, and if I just do r locus with the transfer function g, that's going to come up with a root locus plot. Let's see if we just get the same answers for the upper and lower stability limits with the root locus plot. Okay, it's a little bit hard to see, so I'm going to zoom in here. This is our temperature sensor, very slow dynamics, and so you can see that off to the left. But I'm just going to zoom in right here, and let's see if we can just pick out some of these points. This is our imaginary axis right here. The y-axis is imaginary, and this is our real axis. So if we have any real parts that go into the right-hand plane, then it's going to be unstable. Okay, and there you can see the gain. We calculated 8.29, and the stability goes onto the right-hand plane right in between those two. Okay, so you can't necessarily zero in right on the value because there's discrete points. But you can see it's going to start oscillating. It's going to create imaginary roots right around a gain of 0.877. Okay, and then you get unstable as well right in between these two. Okay, 0.71 and 0.87. We had calculated 0.79, but you can see where it starts here at the x, and then travels this way as the gain increases, and then starts oscillating. And then you can see where it becomes unstable with the upper limit. This is the 8.29, and this limit right here would be the 0.79. Okay, so that shows you how to do it with a root locus plot as well. Okay, just to get to the problem, I'll just show you the way to get here. Here's the course website, and you can get to it from assignments, and then just scroll down to controller stability limits, and this is problem number 3 that we just covered, and also have the solutions to all of them with additional source code down there below.